Science communication has really moved on in this country in the last decade or so. Certainly when I was doing my PhD and postdoc, I was very much warned against doing too much public engagement. Get the grant applications, get the papers, go to the conferences, and why do you want to go and become a science communicator? Thankfully, that attitude has changed, and universities and more widely, I think we are acknowledging the importance of science communication, certainly even among practicing scientists, whether at universities or working in industry and so on. So I wanted to spend some time talking about a particular challenge. I made a three-part series called Atom about 5 years ago now, and it was my first big sort of presenter series, and it was particularly challenging because we wanted to get across the idea of quantum mechanics and how weird it is, and talk something about atomic nuclear particle physics to a general audience on TV. And it's probably fair to say it hadn't been done really before. I mean, we can go back to very early communicators on TV, Bronowski, Carl Sagan, and so on, who didn't pull their punches. But essentially, it really has been, certainly until the last few years, science on TV has either been, Horizon or Equinox, where they had their own niche and they had their own demographic that they appealed to. Otherwise, it was, Tomorrow's World. Or if you wanted sort of the nitty-gritty, then you sort of stay up till 2 in the morning and watch Open University lectures. I mean, that's the science that was on TV. So this was a particular challenge for me. I don't say any more about how I got to be doing what I'm doing, but certainly I'll leave some time for questions afterwards if you wanted to quiz me on it. I was contacted. I'd done a bit of telly, a bit of as a contributor, a bit of radio and science communication. I was the IOP's Schools and Colleges lecturer in 1997, and that's an annual responsibility that someone's asked to travel around the country talking to 14 to 18-year-olds about physics. And that's really sort of the big science communication activity that got me started. But I ended up being asked by an exec producer, a guy called Paul Sen, whether I'd be interested in fronting a series on quantum mechanics. And he came down and gave me a screen test, and he was looking for other presenters, and I didn't think anything more of it. I assumed it's another one of these things. It wasn't something that had been commissioned. He had an idea. He wanted to put the proposal through to the BBC, commissioning editor, and see what happened. And it was about probably as long as 6 months later that he called me back up again and said, "Jim, it's Paul, great news, we've got the green light." And I had no idea who Paul was and what green light we were talking about. I was completely lost. He said, "Oh, no, we've been doing." I said, and he said, "We want you to present it." I said, "Oh, I didn't realise I was even in the running still, And so Paul Sen, the executive producer, is an engineer. He's got an engineering degree from Cambridge. The director that I worked with on all three parts was a guy called Tim Usborne, who's also a physics graduate from Bristol, and had spent his TV media career essentially editing pop videos for about 10 years. So for him, this was great. He could actually get stuck into doing some physics again. And so between us, I think we really sort of took the bull by the horns and decided we'd put in as much physics as we could get away with, as the BBC would allow us to. So I want to just talk you through some of the trials and tribulations and pleasures and challenges of making this three-part series. I should say, of course, and I want to start, I guess you're mostly physicists in the audience, but I want to start just to get across the challenge of why quantum mechanics is so weird. I'd written a book, which was the book that got Paul Sen interested in getting me on board for the TV program, called A Guide for the Perplexed. And on the back of the book, I had this quote from Niels Bohr, one of the founding fathers of quantum mechanics. "If you're not astonished by quantum mechanics, then you haven't understood it. You're meant to be astonished. You're meant to be baffled. You're meant to be perplexed." We wanted to get across the idea to a viewing audience that you're not going to become experts in quantum mechanics, but you are going to understand why it's so perplexing, why it's so mysterious. And the series was commissioned. It was felt that putting quantum mechanics in the title of the series would have been in itself too scary for people. So the series ended up being called Atom, which is a nice You know, at the time, that was the BBC's, you know, the type of titles they liked, you know, one-word titles, until the Wonders of series of Brian Cox took off. And in fact, so he's done the Wonders of the Solar System, Wonders of the Universe, and in the new year he's got the Wonders of Life coming out, his new series of, which I gather is a lot of, you know, the physics of biology, the physics of life, which will be exciting. But this at the time was called Atom, but we were hoping to get as much quantum mystery in it as possible. I just wanted to spend a few minutes reminding you of why quantum mechanics is so mysterious, and I'll do it using the famous, as Richard Feynman says, this is the underlying mystery of quantum mechanics, what's called the two-slit experiment. So you thought it was going to be a media-type talk, and it ends up being a physics lecture, but no apologies. Begin with something like light. We know light behaves like waves. So imagine you have a source of light. Now, for the pedants in the audience, you'll note that a light bulb gives off white light, which is light of all wavelengths. Let's pretend this is monochromatic light coming with a particular wavelength. It hits a screen with two slits in. The light squeezes through both slits and then diffracts. It squeezes and spreads out. And as it comes out, each slit will then act as a new source on the other side, and these waves will interfere with each other and give rise to what's called an interference pattern. Now, kids at school do this with the ripple tanks, and it's known that this is a classic property of waves, that they spread out and they give rise to these light and dark fringes. If we do the same experiment again, not with waves, but with particles, and I've chosen here grains of sand. So this is the same experiment, but it's been twisted 90 degrees. So we're allowing gravity to pull the grains of sand through, and you don't get grains of sand going through both slits at the same time. You get them, each grain goes through one slit or the other. So you end up with a double bump rather than lots of bumps or, you know, of an interference pattern. So there's wave behavior and there's particle behavior. In the quantum world, things are very different. So if you imagine setting up an experiment where we're firing, say, atoms from some source, some atom gun that shoots a stream of atoms at a screen where the slits are of appropriate width and separation. And to begin with, let's say we know nothing about quantum mechanics. We don't understand what we're going to see, and then we have to try and figure out what's going on. Close one of the slits. The back screen now is some sort of photosensitive screen whereby an atom, when it hits it, it will give off, the material on the surface of the screen will give off a flash of light, so you can see where the atom has landed. Of course, you don't see atoms, they're very small. So the assumption is the pattern here adjacent to the lower slit, there's a bit of a spread. That doesn't necessarily mean there's diffraction going on, because you say if we don't know anything about atoms, these are tiny, tiny particles. Those that go through the slit without bumping into the edges will go straight through and land somewhere in the middle. You've got a few astray on either side. Maybe they've sort of hit the slits, the edges as they've gone through. A lot of atoms, of course, are just going to be blocked by the first screen. That's fine. There's nothing mysterious or magical or weird about that. The weirdness begins when you open the upper slit. Because what you'd expect to see are two lines for the atoms that have gone through the lower slit and the atoms that have gone through the upper slit. But instead, we see something reminiscent of an interference pattern. It's as though there's wave-like behavior taking place, and yet we've got dots, discrete dots, saying these are discrete atoms that have landed in particular locations on the screen. So what's happening? How are the atoms going through these two slits to give us this pattern? If we don't know anything about atoms and how they behave, you can say, well, atoms must be subject to some forces that, whatever they may be, they're complicated, but they give rise to this pattern. Maybe the atoms are bumping into each other, and they're sort of, you know, the interatomic forces are saying that for whatever reason, only a certain number can land together in a particular region, saying, right, me and my crowd are here, you go off somewhere else, and by the way, make sure no one lands in between for some as yet to be explained rule about the way atoms behave. Well, we can try and discount that argument by not sending through the stream of atoms altogether, but send the atoms through one at a time. And only after a certain time do we send the next one through? So if an atom gets through one or the other of the slits, you'll see a spot of light. But if you don't, that's presumably because it's been blocked by the first screen. So you start off sending one atom at a time, and you see them landing somewhere on the back screen. But as we keep on going, you start to see the interference pattern arrive again. So we've got an interference pattern reminiscent of wave-like behavior. And remember, this pattern, this interference pattern, only comes about because you've got things appearing from both slits and interfering with each other, the waves overlapping. But each atom is going through by itself. So each atom is contributing its small part to an overall interference pattern. So if there's wave-like stuff going on, then each atom is doing that. Each atom is behaving in some way like a wave. So what happens is it does the atom, which comes out as a tiny particle, see the two slits and somehow spread out, or does it split into two and then they combine again on the other side? Because clearly tiny atoms coming from there, and we have a point at the back, so it's a particle, and here it's a particle, but somewhere in the middle it's doing something that gives rise to wave-like behavior. Well, we can try and be clever, even cleverer. Let's try and spy on the atoms and see what they're up to. What if we were to stick a detector just behind the upper slit? Now, if you know about quantum mechanics, you know the act of the observer affects the outcome of the experiment. So we're going to assume in an idealized situation that we're carrying out a very subtle, weak sort of measurement detection, whereby this detector will flash or bleep if it detects an atom going through the upper slit, but won't if the atom goes through the lower slit. And run the experiment again, one atom at a time. What you find, of course, at the end, is that half of the time, of all the atoms that have got through, half of them triggered the detector and the other half didn't. That means half of them went through the top slit and the other half went through the bottom slit. So it seems they don't go through both slits at once. They go through one slit or the other. But I've not shown you the screen. I've not shown you what the result of this experiment is. And it looks like that. It's different. We've stuck a detector there, and suddenly, yes, indeed, the 50% of the atoms that have got through the upper slit that trigger the detector have landed adjacent to the upper slit. And those that haven't have landed underneath adjacent to the lower slit. So just by looking as carefully as we can, it seems that we've changed the behavior of the atoms. Okay, how about if I leave the detector there, but I very quietly go and unplug it, so the atoms don't know. As far as the atoms are concerned, I'm still detecting them, right? So they should still behave the same way. Run the experiment again. Now, I don't know which way they've gone, but I've got the detector there pretending that I'm checking. Run the experiment again. With the detector off, bang, the interference pattern comes back again. It's as though the atoms have arrived on this side of the screen, faced with a choice of going in two ways, but somehow having this psychic ability to no, you've got a detector there and it's on. There's no way you're going to catch me out going both ways at once. I'm going to go through one slit or the other. Turn it off. You can't fool me. I know it's off. Yay, I can do what atoms do when you're not looking and go through both slits at once. Well, if anyone, so quantum mechanics has been known for nearly 90 years now. If anyone could come up with a logical, common sense explanation of how the atoms do that, that would be a major breakthrough in physics, actually. Because despite quantum mechanics being the most powerful, probably the most important theory in the whole of science, given that so much of physics, so much of chemistry, electronics, all depend on the rules of quantum mechanics, everything we know about the subatomic world and the technologies that we've developed in the last 100 years or so that have relied on them, all depend on quantum mechanics being right. So we're not in doubt that the mathematical theory makes accurate predictions about the world of atoms and the particles that make up atoms. Yet at its heart, no one can come up with a logical explanation for why this happens. Now, how do physicists cope? Well, if you've studied quantum mechanics, you know there's all manner of ways we cope with it. The standard version is something called the Copenhagen view, and that's because Niels Bohr and many of his young disciples, Werner Heisenberg and Wolfgang Pauli and people like that, all worked with him at his institute in Copenhagen in the mid-1920s. And they got round it. They basically said, don't worry about what goes on there. Here's a theory, quantum mechanics, that predicts what you will see. If you carry out a measurement by putting a screen here, it'll predict you'll get this pattern. If you want to see which way it goes through and you're measuring at this point, it'll predict the interference pattern go. So quantum mechanics predicts, the theory predicts exactly what we see, but doesn't explain how each individual atom gets through. And most physicists use that pragmatic way of dealing with quantum mechanics just in order to get on so they don't, sort of go crazy. And in fact, a lot of physicists have told, generations of physicists have told their PhD students, don't worry your pretty little heads about what's going on, otherwise you might as well go off and be a philosopher, because quantum mechanics as a theory works, and it predicts the behavior of nature, but also tells us that when you try and look to see what's going on, you're going to alter the experiment. There are other interpretations involving parallel universes, involving signals being sent forwards and backwards in time, in terms of what are called quantum potentials that seem to be, be connecting the whole universe instantaneously together. None of them are sort of common sense. None of them are the sort of explanations where you think, I see, that's how it works. So quantum mechanics, that's what I mean by if you're not baffled and astonished by quantum mechanics, then you haven't understood it.